Today we're going to start our unit on the periodic table. There's a couple of scientists that we need to be familiar with that played a very important role in the development of how the periodic table is arranged today. So for Roman numeral 1, the title should be Development of the Periodic Table. And the first scientist that we need to have a little bit of knowledge of is Dmitri Mendeleev. Dmitri Mendeleev is known as the father of the periodic table. You just finished watching a abbreviated introduction to the history of the periodic table, and in that you learned of a dream that Mendeleev had. And so basically, if you look here at this particular picture that I've pulled in here, this is the information that Mendeleev wrote on his note cards that he was using to look for patterns. He wrote the symbols of the elements and he had their atomic weights. But I want you to notice that he didn't have all of the elements that we have today. There were only about 63 elements that existed at the time. And so what he did is he wrote down their symbols and their atomic weights, and also some of their properties were known as well. So what he did is he looked for a pattern. He looked for a pattern that was occurring that potentially would have characteristics of their weights as well as their chemical and physical properties. That is the way that he arranged his periodic table. Mendeleev arranged his periodic table in order of increasing atomic masses and according to similar properties. Now, keep in mind, only 63 elements did they know existed at that time. So his pattern worked very well for a while. But as more elements were discovered and added to the periodic table, there were some inconsistencies with the elements being in order of their increasing atomic weights. And one of the first scientists to recognize that was Henry Mosley. He was a very young scientist, and what he did is he noticed that there were a few places where the atomic weights were not increasing as you went across the rows. So what he did is he proposed that what if we look at, instead of the atomic weights, look at the atomic number. Now remember, the atomic number is the number of protons in the atom. Now, when put in order of increasing atomic number, the elements are still going to be in order of similar properties, chemical and physical properties. This is actually how today's modern periodic table is arranged, in order of increasing atomic number, so in order of increasing number of protons, as well as similar chemical and physical properties. So this leads us to another scientific law that we need to be familiar with. It's called the periodic law. The periodic law states that when the elements are arranged in order of increasing atomic number, there is a periodic pattern in their physical as well as their chemical properties. So when the elements are arranged in order of their atomic number, there is an underlying pattern. Not only do they fall in columns where they have similar physical properties, but also chemical properties. And in this unit, we are going to learn about the structure and the patterns on the periodic table. Now, I told you early on that in chemistry, if you could learn how to master your periodic table and how to master your calculator, you could master chemistry. So in this unit, we are going to be learning about some of the very important things that you need to know in order to master that periodic table. So the modern periodic table is arranged by periods, Periods are the horizontal rows. And they're organized by groups or families, and those are your vertical columns. And we briefly touched on this in the first unit, but we're really going to focus on it in this unit. So let's talk about those groups or families. The periodic table, on the periodic table, the groups or families are identified by number-letter combinations. Now, it's not just a regular number, they're Roman numeral letter combinations. When you look at your periodic table, and it would benefit you to go ahead and have that out, take a look at your periodic table. There are two ways or two groupings, if you will, of how we can talk about the families. We can refer to those that are called the representative elements, and those are the ones that have Roman numerals 1A to 8A. On your periodic table, those are the tall columns. Now, if you pay attention to the representative elements, the taller columns, the representative elements, the numbers 1A through 8A, that Roman numeral that's in front of the A tells us a very important piece of information about our atoms. What it does is it indicates for us the number of valence electrons in the atom. Now, this pattern only works for the representative elements, and those are the ones we're going to really focus on in this unit. There's another group of elements that we can refer to as the transition elements. Those are the group B elements. They're not going to have a capital A, Roman numeral 1A to 8A. They're going to have Roman numerals that end up with B's with them. They're the B elements or the transition elements. The elements in this group don't really follow a specific pattern. And what we're going to do in this particular unit is we're going to focus on the representative elements, the ones that do follow a particular pattern. So later on in a different unit, when we've learned more about the structure of the atoms and we talk about electron configurations, we'll talk more about the group B elements then and the patterns that they form. So I just mentioned that the group number, the Roman numeral 1A to 8A, indicates for us the valence electrons in an atom. So let's talk about what exactly a valence electron is. The valence electrons are the outermost electrons in your atom. So if you think about, if this little dot here represents a nucleus of an atom, and we will be practicing Bohr models later, but let's just, for the sake of talking of Bohr models, let's just look at an atom that has 3 energy levels around the nucleus. So within the energy levels, that's where you have the electrons. Well, the valence electrons are the ones in the outermost energy level. So the valence electrons will be found in the outermost energy level. So like right here would be 1 valence electron. And if you have 1 valence electron, that means the element is in group 1A. Now keep in mind that the inner energy levels, so this being the first energy level and the second energy level and the third energy level, when you're filling up your energy levels, you do have to fill up the first energy level first before you go to the second and then before you go to the third. But specifically right now, what I'm talking about are just the valence electrons. So valence electrons are the outermost electrons in your atom. Now, the reason that they're so of interest to us is because those are the electrons that are available to be gained, lost, or shared. So if you gain or lose electrons, we talked about this in the last unit, that's when you form anions and cations. But when electrons are shared, that's when chemical bonds form. So like when carbon and oxygen react to form carbon dioxide, or when hydrogen and oxygen react to form water, or when sodium and chlorine react to form sodium chloride. So the valence electrons are important to us or of interest to us because their arrangement in the atom leads to their chemical and physical reactivity, and they're also the ones that are going to be the first electrons to be gained or lost or shared. So we need to be able to interpret or to speak of how many valence electrons an atom has. So the number of valence electrons in your element is always equal to the group number for those representative elements. The number of valence electrons is equal to the group number for the representative elements. Now, one thing that you want to keep in mind is all atoms want to be stable. Now, for atoms, where the electrons are located in their outer energy level, that is a big indicator of whether or not they're going to be stable in their elemental form. So if it's just the element existing. All elements want to have 8 valence electrons in their outer shell. Now, I say all. There's a couple of exceptions to that rule, but in general, the rule of thumb is in order to be stable, the atoms they need to have 8 electrons in their valence shell. So the 8 is an important number here for stability. Just like we like to be stable, we like to be happy, the atoms want to be happy. And the way that they get happy is to get their outer electrons arranged so that they have 8 in the outer shell. They want a full valence shell. They want a full valence shell. They want it to be full. So we say that they obey the octet rule. Think of 8, an octave, an octagon, an octopus, 8. They want to obey the octet rule. So in other words, they want to be like the happy family. Now we're going to learn in this chapter the family names, and we're going to learn that the happiest family on the periodic table, the most stable family on the periodic table, are the noble gases, and they happen to be in group 8A. Now remember, the group number tells you the valence electrons, and the noble gases, with the exception of one, helium, they have 8 valence electrons. So this is our very first pattern that we want to write down. Now, I've got the numbers 1A to 8A, 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And this corresponds to the group number. So if you look on your periodic table and you know the group number for the representative elements, and again, the representative elements are the A elements, 1A to 8A. If you know the group number, you can also predict the number of valence electrons. So group 1A has 1 valence electron. The elements in group 2A have 2 valence electrons. The elements in group 3A has 3, 4A has 4, 5A has 5, 6A has 6, 7A has 7, and 8A has 8. Now, there is one exception there to that, and the only exception is helium. He does happen to be in group 8A, but he only has 2 valence electrons. We'll learn more about that later. All right, so that was the first pattern that you want to know. Now, the second pattern has to do with the ionic charge pattern on the periodic table. Now, what I want you to do is to have your periodic table out, and I want you to make sure that you're labeling this on your table as well. So first we're going to put it in our notes, then we're going to put it on your periodic table. So I've brought in a periodic table here that's not exactly like the one that y'all have, but it's very similar. So I want to first off number the Roman numerals. So this is Roman numeral 1A. This is Roman numeral 2A family. This is group 3A, group 4A, group 5A, group 6A, group 7A, and group 8A. So Roman numeral 1A, to 8A. Those are the representative elements. Now the B elements that I was speaking of earlier, these are these transition elements here. These are the B's. And they don't really follow a pattern, so for right now, we're not going to worry about those. We're going to focus on the A elements. So let's talk about the charge pattern. Now, one thing I want to mention, and I'm going to go through this slowly to begin with, but I want you to keep in mind that every element wants to be like a noble gas. So keep that in mind. I'm going to box in these noble gases here. Every element wants to be like these noble gases over here. So what does that mean? They want to try to get to where they have 8 valence electrons. All right, let me try to erase some of that. They want to get where they have 8 valence electrons. So let me try this again. Every element wants to be like this family, the noble gases. This might work better. Every element wants to be like the noble gases. They want to have 8 valence electrons. So if you think about the periodic table, let's assume that we're traveling up and down the periodic table. So we'll say we're traveling the streets of the periodic table. Okay, so like lithium, let's look at lithium. He's in group 1A. He has 1 valence electron. Lithium would like to look like a noble gas. So he's got 2 options. He can either lose his 1 valence electron, and if he loses his 1, he goes from 3 to 2, and he would look like helium. He could lose 1, or he could gain 1, 2, 3, 4, 5, 6, 7, and he could look like neon. Now, what do you think would be faster, to lose 1 or to gain 7? Well, of course, it's going to be easier to lose just 1. Lithium will always lose 1 valence electron. He will go from 3 to 2, and that will make him have a positive 1 charge. Remember, if you lose 1 electron, 1 bad habit, you get positive 1 charged. Every element in group 1A, when they form an ion, they will always form a positive 1 charge. Every element, when they form their ion, they will always form a positive 1 charge. So write that in. I'm going to try to, all right, so positive 1. Sodium, same thing. Sodium can either lose 1 and go from 11 backwards to 10 and look like neon, or he could gain 1, 2, 3, 4, 5, 6, 7. It's a lot faster to lose 1 than gain 7. Everybody in group 1A will form a positive 1 charge when they form their ion. Now let's look at group 2A. Group 2A, right here, beryllium, he could either lose 1, 2, and look like helium, or he could gain 1, 2, 3, 4, 5, 6. All right, lose 2 or gain 6. Again, it's going to be easier to lose 2. So if beryllium loses 2 bad habits or 2 valence electrons, he becomes positively 2 charged. So everybody in group 2A will form a positive 2 charge to form their ion. They all have that in common. That is a pattern. Let's come over here to group 3A. So let's look at, we'll look at aluminum. Aluminum has 3 valence electrons. He's got 13 total electrons, but 3 of them are his valence electrons in his outer shell. He could either go backwards 3 from 13 to 12 to 11 to 10. He could go backwards 3 and look like neon, so he could lose 3, or he could gain 1, 2, 3, 4, 5. Now again, they're going to do what's faster and what's easier. So aluminum is going to form a positive 3 charge, and so will everybody else in this column. They're going to lose 3 valence electrons and become positively 3 charged. So right now the pattern is +1, +2, +3. So if you know the pattern, I could ask you, hey, what charge will indium form when he forms this ion? And you could say, well, based on his position, it's going to be a +3 because everybody in this column forms a +3 charge when they form their ion. That's how they get stable. All right, let's look here at carbon's family. This is group 4A. So carbon's family is kind of in the middle. They can either go forward 1, 2, 3, 4, or they can go backwards 1, 2, 3, 4. So for this family, I want you to put plus or minus 4. Now we're going to come back to the carbon family after I show you the rest of the pattern, and I'm going to talk more specifically about the elements in this column because some of these do +4 and some of these will do -4, and I will tell you how to figure it out in just a second. All right, let's go on to nitrogen's family. Nitrogen can either go forward 1, 2, 3 and gain 3 electrons or pick up 3 bad habits, or he could lose 1, 2, 3, 4, 5. Now again, they're going to do what's faster. It's easier for nitrogen to go forward 1, 2, 3. That's shorter. So he's going to gain 3. So everybody in this family is going to be a -3 charge. Oxygen's family is going to gain 1, 2. They're going to go forward 2 and gain 2. So they're going to all form a -2 charge for this family. And everybody in fluorine's family is going to be a -1 because they're just 1 away. They need to gain 1 electron and they'll be just like the noble gases. So look at your pattern. +1, +2, +3, plus or -4, -3, -2, -1. And the noble gases, guess what? They're already stable. They do not form ions. They're a 0. They do not form ions. They're already stable. Therefore, there's no reason that they would need to gain or lose electrons because they're already the happy family. They're the stable family. They're the noble gases. Now, I mentioned that I would come back to the carbon family. I want you to notice something about carbon's family. Carbon is a nonmetal. And then you've got silicon and germanium that are metalloids. And then you've got tin and lead and flavorium that are metals. Notice this family here has a mixture of metals, nonmetals, and metalloids. So this family is a little more complicated. What I want you to remember is something we learned in the last unit. We talked about cations and anions. We said that cations are always formed by metals. And we said that anions are always formed by nonmetals. We learned that in the last unit. So let's look at this. Carbon is a nonmetal. That means carbon is going to be a -4 when he forms his ion. So I want you on your periodic table where carbon is in the square, I want you to write as a superscript -4, teeny tiny in the corner. Now, we're not going to worry about silicon and germanium right now because they're metalloids. We're going to come down to our two metals, tin and lead. These are the metals. So since they're the metals, they're going to be the +4. So I want you to write +4 in their squares to remind you they're the +4. So you need to remember for the carbon family, they can't do either or. Carbon does like the nonmetals. See, all these are nonmetals here. The nonmetals always form anions, and the metals form cations. So tin and lead are going to form +4 charges. All right, so that is your charge pattern. The charge pattern again is +1, +2, +3, plus or -4, -3, -2, -1, and 0. Groups 1A to 8A. The next pattern we're going to look at has to do with your periods. The periods on the periodic table are numbered 1 to 7. They're numbered 1 to 7. The period number indicates the number of energy levels around the nucleus in the atom. The period number tells you how many energy levels to draw around the nucleus of your atom. Now, why is this important? Because when we draw Bohr models, we need to know how many energy levels to draw around the nucleus. So I'm only going to draw a couple of Bohr models with you on this part of the video lesson, and then there will be some more that you will do later for part of your homework. But you're going to want to have your periodic table handy to look at. All right, hydrogen. When you draw a Bohr model, I always like to start with the nuclear notation. So if we look at the nuclear notation for hydrogen, it would be 1 over 1 H. So we just finished with nuclear notation in the last unit. Also, something else you want to know is that hydrogen is in period 1. So if you look on your periodic table, it's in the first period. Now, if you look at your proton, your electron, and your neutron count here, hydrogen, according to this, has 1 proton. And this is an atom of hydrogen, so he also has 1 electron. Remember, to get your neutrons, you say 1 minus 1 is 0. So he has 0 neutrons. Now, this circle represents the nucleus. So what I want you to do when you draw your Bohr model is I want you to put the nuclear contents. So you have 1 proton and you have no neutrons in the nucleus. Now I'm going to change colors so I can distinguish between my energy levels. Since hydrogen is in the first period, so look to your periodic table and see what I'm talking about. He's in the first period. He has 1 energy level. So I'm going to draw the 1 energy level around the nucleus. Now, when you're filling up your energy levels in your atoms, you want to remember that you have to put 2 electrons in the first energy level, 8 can go in the next energy level, and then 18 can go in the third. Now, we're not going to draw any past the third energy level. But here, we just have 1 energy level because it's in the first period. It has 1 electron, so we're going to draw the 1 electron here. Okay, and that dot represents the 1 electron. That is his valence electron. Now remember, hydrogen should have 1 valence electron because he's in group 1A. He's in group 1A. So we should have 1 valence electron, and that's it. Now, if you were going to draw the electron dot structure for this, you would put the symbol for your element, hydrogen, and you would put a dot for every valence electron. Since hydrogen has 1 valence electron, you would put 1 dot. This is called the electron dot structure. This is the Bohr model. All right, let's take a look at helium. So helium is 4 over 2 He. That's the nuclear notation for helium, 4 over 2 He. All right, so let's look at our proton, electron, and neutron count. He has 2 protons. There, he has 2 electrons because it's an atom. 4 minus 2 gives you 2 neutrons. So we're going to draw the nucleus again. And I'm going to draw the nuclear contents. He has 2 protons and 2 neutrons. Now, take a look at the period that helium is in. Helium is in period number 1, just like hydrogen. There are only 2 elements in the first period. That means he's going to get 1 energy level around the nucleus. Now, we're going to look, he has 2 electrons. So we're going to put his 2 valence electrons, 1, 2. So that is helium, Bohr model. If you draw his electron dot structure, you would put He, 1, 2. Just put 2 dots. All right, we're going to do lithium next. Let's look at lithium. Lithium is 7 over 3. So we've got 3 protons, 3 electrons, and 7 minus 3 is 4 neutrons. All right, so let's take a look at also the period that lithium is in. Lithium, if you look at his period, is in the second period. So period number 2. That means he's going to have 2 energy levels around the nucleus in just a second. So here's the nucleus. We said we have 3 protons. We have 4 neutrons. And now we're going to draw the energy levels. Since he's in the second period, we're going to draw 1, 2 energy levels around the nucleus. Now, let's place our electrons. We just said he has 3 total electrons. So you put 2 electrons always go in the first energy level. That's the most that the first energy level can hold, 1, 2. And now you put 1 in the second energy level. This is his valence electron. This is his valence electron. He is in group 1A, so he should have 1 valence electron, and he does. Now, if you want to draw the electron dot structure for lithium, you would put Li, the symbol, and remember you only show the valence electron, so you would draw 1 dot to be his 1 valence electron. We're going to do one more example together right now for oxygen, and that's where I will leave off for today with this lesson. So let's look at for oxygen, let's look at his nuclear notation. It's going to be 16/8O. I'm going to go ahead and indicate he's in period number, if you look, 2. And his group number is 6A. That's important for drawing the Bohr model. Period 2, 6A. Proton, electron, and neutron count. He has 8 protons, 8 electrons, and 16 minus 8 gives you 8 neutrons. Let's look at the nucleus. We're going to put his 8 protons in the nucleus. We're going to draw his 8 neutrons in the nucleus. Now, since he's in the second period, how many energy levels should we put around the nucleus? That's right, he's got 2. So we're going to go 1, 2. Okay? Now, in the first energy level, how many electrons can fit? In the first energy level, how many electrons can fit? That's right, 2. So 1, 2 electrons in the first energy level. And now we're going to put the remaining electrons in the second energy level. Now remember, the second energy level can hold up to 8. We've already got 2. He has 8 total. That means we need to put 6 more in the second energy level. So when you put them in the second energy level, start at 12 o'clock, go to 3 o'clock, go to 6 o'clock, go to 9 o'clock. So 1, 2, 3, 4. And we had 6 to put here. So come back up here, start pairing them up. There and there. So 1, 2, 3, 4, 5, 6. That gives you 6 valence electrons, and he's in group 6A, so he should have 6 valence electrons. Now, if you're going to draw his electron dot structure, you're going to put O, and you're going to put 2 electrons, up top, 2 electrons here, 1 here, and 1 here. It's going to mimic what the outer shell looks like here. All right, so we'll practice some more of these later. That's all for today for Bohr models.